Hey guys, this is an explanation and proof for theorem 10.3, which is in your book in section 10-3 on page 535. This is what it says. In a circle, like this one, if a diameter, so here we have a diameter, or radius, is perpendicular to a chord, then it bisects the chord and the arc. Okay, so we have a diameter, we have a chord. Notice there's a 90-degree angle, so perpendicular means they form a 90-degree angle. What's going to happen is this diameter is going to cut chord AB into two equal halves, which means that AC will be congruent to CB. Okay, it will also bisect this arc AB. So DE, that diameter, will bisect AB so that the measure of AE and the measure of BE are equal to each other as well. Okay, so we're going to prove that in just a second. In order to prove that, though, we need to talk about a triangle congruence postulate that we haven't talked about before. Okay, so I'm going to come back to this. I'm going to flip over, and I want to talk about triangle congruence postulates and theorems that we know so far. Okay, this is something we talked about in class. So if you were in class on day one of this week, then you probably already saw this, but this is kind of for people who missed it, or if you want to go back and review. Okay, so what we know already is we can show two triangles are congruent if we have three sides of one triangle congruent to three sides of another triangle. Also, if we have two sides and an included angle of one triangle congruent to two sides and a congruent angle of another triangle, we can show those triangles are congruent. We call that side angle side for short. Okay, we have a couple other ones, angle side angle, right, and angle angle side. Okay, so those are the theorems and postulates that we use to determine if two triangles are congruent, or shortcuts that we use. Okay, let me show you what's not one. And this is kind of silly the way I write it. I do this on purpose because I want you to remember that that is not congruent, or that is not a congruence theorem. It's not a valid congruence theorem or postulate. So don't write this on your paper, and when you see it written on your paper, you're like, wait, there's got to be something wrong because I'm not supposed to write that. Okay, so this is actually not one of them. Okay, let me show you why. So I'm going to do a counter example for ASS. Okay, what I'm going to do is I'm going to show two triangles that have ASS in common and show that they're not actually congruent. Okay, so this is how we do that. I'm going to start by sketching out a little triangle here. Okay. Okay. Now use your imagination for a second and pretend that this leg is on a little hinge. In other words, that it can swing back and forth. So I can move this guy over here almost like the hand of a clock or something like that. If I were to do that and move it over, it would kind of go and would arc around, and eventually it would line back up with the bottom side of the triangle. Okay, let me get a little closer for you. Okay, so notice that when I do that, there's like a few different triangles here. There's the original triangle, this guy, and then there's this one that's kind of inside of it. Okay, if I redraw those two triangles separately, you'll kind of see why angle side side doesn't work all the time. Okay, so let's draw the original one back. Do the best we can here because sometimes that's hard to make an exact copy. Something like that, right? And the new triangle that I drew is this one, the one with this guy as a side. So it's got like an obtuse angle, right? And it kind of fits inside this one. Now I know that's not perfectly to scale, but that's kind of the idea. Now because these two triangles came from this guy, what I know is that this angle and this angle are exactly the same. Right? Because they're both that guy. Imagine I just took that triangle and put it down here, and then took the full triangle and put it down here. This angle is the same on both of them. Okay, the other thing that's the same is this guy, right? Like that hasn't changed. This piece is a part of both triangles. It's a part of this guy, and it's a part of this guy. So this side is congruent to this side. Okay, the other thing I know is these two guys are the same length. Because I didn't really change the length, I just changed the angle. So imagine again, without changing the length of this guy, I just swung it over so it's the same, length. So this guy's congruent to this guy, right? So there's, two ways to draw this guy so it's the same length and still matches up with this side. There's two versions here. Now, obviously, these two triangles are not the same because one fits inside the other, right? They can't be congruent if one fits in. I mean, it doesn't fill the whole space, right? Like it's smaller than the original, okay? So these two triangles, notice, have angle, side, side in common, but they're not the same triangle. There's two different versions that have the same angle, the same side, and the same side, and they're not the same. Okay, so angle, side, side does not work all the time, which is why it's not on our list. Okay, now there is something that you can use that's kind of similar to this that we haven't talked about before. Okay, and that's called the hypotenuse leg congruence postulate. Okay. Now, if you think about hypotenuse, leg, when you hear those words, you start thinking right triangle, because not every triangle has a hypotenuse, just right triangles do. So let me give you kind of a different example of what's going on here. So let's say I have kind of a similar scenario, but this time the angle that I know is a 90-degree angle. Okay, so 90, 90, right? And let's say that I know this guy is congruent to this guy, and this guy is congruent to this guy. Okay, so what I have is the two hypotenuses are congruent to each other, and then I have a leg congruent to another leg. And then I have a right angle. These triangles will always be congruent to each other if they're right triangles. Because think about like the Pythagorean theorem. Let's say this is 5, and this is 5, and this is 3, and this is 3, right? There's only one other option for that third side if you use the Pythagorean theorem. It's got to be 4 and 4, right? That's just kind of how it is. So right triangles are special. Notice, though, I have what looks like ASS, right? Angle, side, side. So it kind of looks like angle, side, side, but angle, side, side doesn't work for all triangles. It only works if you're talking about a right triangle. Okay, and so we don't say angle, side, side. We say hypotenuse, leg, because only right triangles have a hypotenuse. So this is how the theorem goes. If the hypotenuse of one triangle is congruent to the hypotenuse of another triangle, and one of the legs of that triangle is congruent to one of the legs of the other triangle, then the two triangles have to be congruent. Okay, this is the minimum amount of information we need to show that two triangles are congruent. That's called the hypotenuse leg congruence postulate. So we can add to our list HL for hypotenuse leg, and we can only use that when we have right triangles, and then it works. Okay. Now let's go back to where we were here and talk about the theorem we were trying to prove. Okay. So totally, different scenario, but we're going to use hypotenuse leg here. So in a circle, right, we have a diameter, and it's perpendicular to a chord, so we know it bisects the chord. All right, so here's the trick here. What we're going to do, just like last time, is we're going to add some radii. Radii is plural for radius. So it's kind of weird to say radiuses. So you say radii. Okay, so there we go. Now, what we have when we get there is that these have to be congruent to each other, obviously, because they're radii of the same circle, so they have to be congruent to each other. And then these two triangles that are formed when I draw those are also sharing this side. Okay, let's label that center point F. So what we're going to do is we're going to show these two triangles are congruent, which means that these two segments have to be congruent. Okay, so let's go ahead and write out the proof here. All right, SR. Okay. Step one. Oh, sorry, we forgot to talk about the given and what we're trying to prove. So sorry, given, we know that DE, the diameter, is perpendicular to AB, the chord. Okay, what we're trying to prove, there's actually two things we're trying to prove. We're trying to prove that the diameter bisects the chord and the arc. Let's start with just the chord for a second, and then we'll go and add to that. So what we're trying to show is that AC is congruent to BC. Right? This little guy is congruent to this guy. If that's true, these two things are congruent, then that means that this is cutting AB into two equal halves. So showing AC is congruent to BC is enough to show that DE is bisecting AB. All right, so let's start with the given. We got DE congruent to AB. Okay, given. All right, step 2, we're going to start talking about the radii that we added. Okay, so we're going to say AF is congruent to BF because they're radii of the same circle. So all radii of a circle are congruent to each other. Okay, we can also say that FC is congruent to FC. Right? Remember, this segment here is actually a side to both of these triangles. So that's the reflexive property. Okay, now here's where it all comes together. Normally we wouldn't have enough information to say these two triangles are congruent because we would say, oh, we got a right angle, right, angle side side, and we can't use angle side side. It's like not a thing, right? But we can use hypotenuse leg here. So we got hypotenuse, we got leg, we know it's a 90-degree angle. So that's kind of the hack here that we have. We got triangle AFC is congruent to triangle BFC. And we know that's true by our new postulate that we just talked about, hypotenuse leg. So that's kind of why we needed that one today. All right, now if that's the case, if these two triangles are congruent, then their corresponding parts are congruent, right? So if these two triangles are congruent, then AC matches up with BC. Those guys have to be congruent to each other. So AC congruent to BC. And we can say corresponding parts of congruent triangles are congruent. Okay, so we're pretty much there. Now, there's an extra piece to it because we haven't showed the arcs are congruent yet. Okay, so let's go ahead and just add a few more steps here. We already showed that AC is congruent to BC. That's part of it. Okay, let's go ahead and talk about these arcs. We want to show that this arc's congruent to this arc. Okay, now we can do that if we know their central angles are congruent, which we actually do, because again, these are congruent triangles. And so we can talk about those central angles, AFC and BFC. So angle AFC is congruent to angle BFC. Again, that's CPCTC. We already know the triangles are congruent, so we can conclude that that angle and that angle are congruent. All right. We also know that the measure of AFC is equal to the measure of arc AE, because remember, a central angle is equal to the measurement of the arc. So the measure of angle AFC is equal to the measure of arc AE. So this arc measurement and that angle measurement are the same. In the same line, same reason, we can say that angle BFC is equal to, the measure of BFC is equal to the measure of arc BE. Okay. And we can do that by, basically we know it's the definition of arc measurement, right? The arc measurement is equal to the central angle. So I'm going to do def of arc measurement. Okay, I think I'm getting a little bit ahead of myself, so let's back up here and just kind of add what we're trying to prove because I forgot to do that. One of the things that this says is that if the diameter is perpendicular to the chord, it bisects the chord and the arc. We already showed in step 5, we already had that this guy bisects AB because AC and BC are equal to each other. Okay, now what we're trying to show is that AE is congruent to BE, the arcs. Okay, so let's add what we're trying to prove. AE is congruent to BE. Okay, so that's where we're going. I kind of jumped the gun and I started adding lines, and you might have been like, why are we adding lines? Well, remember there's two parts to this. It bisects the chord and its arc, and so we In step 5 we had this. Now we're trying to go to this. Okay. And again, if we can show that this and this are equal to each other, then we know this cuts it in half. All right. So what we got, we're pretty much almost there. I kind of neglected one line here that we need. We can add that here now if we need to. But we know these angles are congruent, AFC and BFC. We already know those are congruent, which means their measurement's the same. So this is more of like a technicality than like a super important concept. The definition of angle congruence means their measures are the same. Sorry, this should be an equal sign, and this should be measurement. So these two lines probably should normally go together. It doesn't really matter, but if the two angles are congruent, their measures are the same. The only reason I need that is because I'm going to do a substitution in a second. Okay, so if these two angles are congruent, then their measures are equal. Sorry, let me rewrite that whole thing. Measure of angle AFC equals the measure of angle BFC. Okay. Now, if that's the case, I can also substitute this arc in for that angle and this arc in for that angle, because remember, the measure of the arc is equal to the measure of the central angle. So I'm going to do that substitution now. So I'm going to replace the measure of AFC or AFE with the measure of arc AE, because this angle and this arc are the same measurement. Okay, that means I'm going to replace this guy, the measure of BFC, with this arc, BE. Okay, that's a substitution. Okay, and the last thing is just to say that AE is congruent to BE. All right, I already know their measurements are equal, but I'm just going to go that one step and say that they're congruent. Again, definition of congruent. Okay, so sorry that got a little bit messy, but that's the rest of the proof. Okay, let's run through that again, just to make sure we have the right idea. Okay, we start out with basically the radius and the right angle. Okay, we got the diameter, makes a right angle with this segment, and then we draw the radius lines. Okay, so from there we say, okay, these two triangles must be congruent. How do we know? Because the two radii match each other, and the triangles both share this side here. So hypotenuse leg, right? Hypotenuse leg gives us that these two triangles are congruent. That's a key. So step 4 is one of the super key ideas. Okay, now from there, we say, okay, if the two triangles are congruent, then their corresponding parts are congruent, which means these two segments are congruent. Awesome. Now we know that DE bisects AB. Okay, the second part is to get the arcs, this arc bisected, or in other words, AE congruent to BE. Okay, so what we do is say, okay, again, going back to the triangles are congruent, which means these two angles are congruent because they're corresponding angles of these triangles. And if these two angles are congruent, then these two arcs must be congruent, because remember, the arc measurement matches the central angle. Okay, so there's a couple like steps in here where you're just moving stuff around, changing stuff from congruence to equality, just to get the substitution thing to happen the way you want it to. But that's kind of the gist of it. Congruent triangles gives you congruent parts, segments here, angles here, and then the congruent angles give you the congruent arcs. Okay. All right, I hope that helped. And if you didn't have that in your notebook already, that's probably a good idea to include in there so you can use it on a test or quiz if you need to. Thanks for watching.